All right, continuing on with our slides for chapter 3, where we left off, we were just about to hit this question, number 21. Now, before you try to pause and do this problem on your own, I need to explain a few things about how to calculate average atomic mass. Okay, average atomic mass has a general form. Okay, general form of the equation. Okay, and the way this works is that for however many isotopes you have, you'll take the mass of, let's say, the first isotope, isotope 1, times its abundance, plus the mass of isotope 2 times its abundance, plus the mass of isotope 3 times its abundance, for however many isotopes you have. Okay, if you have 5 isotopes, you have to do this 5 times. If you have 2 isotopes, you do this 2 times. And this all comes out to be the average atomic mass. And guess what? The average atomic mass is what you find on the periodic table. Okay, so if you're asked to calculate the average atomic mass, you have to show your work. Okay, it's not enough to go looking on the periodic table. You have to show your work. Okay, because we also might put you in a situation where we'll give you the average atomic mass and you have to figure out one of these other numbers. Okay, one of the other numbers for one of the other isotopes. So mass times abundance plus mass times abundance for however many isotopes you have. Now, the other thing to know is that the abundances have to be in decimal form. That is not how you spell abundance. Abundance in decimal form. Okay, and the way you go about that is you take the percent, divide by 100. Okay, so in this case, if I have 75.76% divided by 100 will give me 0.7576. Okay, so now that we know that, let's go ahead and tackle this problem. Okay, so we have chlorine 35, and it has a mass of 34.969 AMU. So that's isotope 1. So 34.969 AMU times the decimal of that percentage, so 0.7576. So this is all for chlorine 35. That's our first isotope. Plus the information for the second isotope, 36.968 AMU, times its abundance in decimal form, so 0.2424. This is all for chlorine 37. That's our other isotope. So we have a sig fig issue. Okay, so we still have to pay attention to sig figs, right? So when we do this part, we're going to get a number that has 4 sig figs, and it will end up with 2 decimal places. All right, same thing for this side. We'll get 4 sig figs and 2 decimal places. Right, and when we add these together, then we apply the addition rule, so our final answer should come out with 2 decimal places. So we end up with 35.45 AMU. And if we look on the periodic table, we will find that that is, in fact, the number that is given. Okay, so the important takeaway from this process is that the average atomic mass is what we call a weighted average. Okay, it's a weighted average of all of the naturally occurring isotopes for that element. Let's check our work. 35.45 AMU. We are correct. All right, let's move on to question 22. Now I want you to go ahead and give the video a pause and see if you can reason this one out. All right, so we are back. Now, remember that number 79 and that number 81 are the mass numbers. Okay, so that means protons plus neutrons, and each proton and each neutron weighs about 1 AMU. So if I have a mass number of 79, then I'm going to have a mass, an actual mass, that is close to 79. Same thing with 81. So if the average atomic mass is 79.90, that one's leaning a little bit more towards the 79 than it is the 81. Okay, if we had more of the 81, then that average atomic mass should be above 80. Right? So we're going to have slightly more of the bromine 79 than we do of the 81. So sodium only has one major isotope. So how many neutrons does this isotope contain? So take a second and find sodium on a periodic table. And you'll find that sodium has 11 protons. Okay, now in order for it to be an isotope has a different number of neutrons. Different number of neutrons. Okay, so that immediately counts out 11 as one of the answers. Now, these numbers 22 and 23 are double or more the number of protons. You'll never find an element that has twice as many neutrons as it does protons. Those do not exist. Okay, 22 and 23 are more like mass numbers, like the addition of protons plus neutrons. So those are going to be out. So we can reason that our correct answer is 12 neutrons. Okay, so this table is sort of a summation of the important models of the atom throughout the ages. Okay, starting with Dalton's atomic theory in 1808, and he had the concept that atoms are indivisible pieces, right? The smallest indivisible unit of matter. And then 100 years later, roughly, we had the plum pudding model, because at this time they had figured out the existence of electrons, and they knew that atoms were electrically neutral, so that meant that there had to be an equal amount of positive charge, but they didn't yet know about the nucleus. And then not too long after that, we have what's called the Bohr model, named after the physicist Niels Bohr. And by that time, they had discovered the nucleus. As you can see, the nucleus is that central little nugget right in the middle of the drawing there. And his idea was that the electrons orbited around the nucleus, much like the planets revolve around the sun, in very defined circular orbits. And then, again, not too long after that, we have what's referred to as the quantum model. And with advances in quantum physics, getting away from relativistic physics, or excuse me, traditional physics, they discovered that electrons behave as both waves and particles. And so they determined that instead of defined circular orbits, they have what are more like fuzzy areas of electrons. Okay, places where you're most likely going to find an electron. Now, atoms can gain or lose electrons, right, depending on whether they are a metal or a non-metal. So remembering from earlier slides, or earlier videos, metals lose electrons, always. Okay, metals never gain electrons, they only lose them. Non-metals, on the other hand, do exactly the opposite. Non-metals only gain electrons. Okay, so if you remember that protons are positive, that's the ones in the middle here. Electrons are negative. Okay, so when a metal starting out neutral loses some negative charge, that means you have more positive left over. So metals make positive ions. Okay. Non-metals, if they start out neutral and they gain some negative, they gain some electrons, non-metals make negative ions. All right, so question 24, the blank described electrons orbiting the nucleus like planets orbiting the sun. So we can immediately, so we haven't really talked about the Rutherford model, so that's going to be not fair game. So the plum pudding model was the one that hadn't yet discovered the nucleus yet. So how could they describe electrons orbiting a nucleus if they didn't know what a nucleus was yet? So we can count that one out. Now the Bohr model or the quantum model. The quantum model was the last one that talked about electrons being sort of fuzzy orbitals. So our final answer here is the Bohr model, named after Niels Bohr. All right, 25. An ion has 11 protons, 12 neutrons, and 10 electrons. Which symbol best describes this? So right away from 11 protons, we know for sure immediately what the answer is. The number of protons can only be for one particular element. And the only element that has 11 protons is sodium. So since we already know this is the correct answer, but let's talk about the rest of that notation there. Okay? So the number 23, that's the mass number. And I want to make it clear that the mass number is not the same as the mass. So the number on the periodic table below the symbol, that's the mass. The mass number is protons plus neutrons. The number of protons plus neutrons. Okay? So if we have 11 protons plus 12 neutrons, we have a mass number of 23. Now let's talk about this plus symbol. So if I have 11 protons, so 11 pluses, and 10 minuses, 10 electrons, if I put those together, that ends up with a +1. And I have one more positive charge than I do my negative charges. So that's why we have our plus symbol. All right, so 26, we're going to write the symbols including atomic number, mass number, and charge for the atoms containing these particles. Okay, so for part A, 4 protons, the only element that can possibly ever be 4 protons is beryllium, Be. Okay, so that's our atomic number. The number of protons is the atomic number. So now the mass number is 4 protons plus 5 neutrons. Gives us a mass number of 9. Okay, and then let's figure out the charge. So I'm going to go below here. So if I have 4 pluses and 2 minuses, so 4 protons, the protons are positively charged. 2 electrons, the electrons are negatively charged. That means I have a positive 2 plus. Okay, so our final symbolization, the mass number goes above, the atomic number goes below, so I'll have 9 above, 4 below, and then it has an overall charge of 2 plus. All right, let's look at B. So 17 protons can only be, with an atomic number, 17 protons can only be chlorine. If you know the number of protons, you know the element. End of story. Okay, and then our mass number, protons, number of protons plus number of neutrons. So I get 17 plus 20 gives me a mass number of 37. And then let's look at our charges. So I've got 17 protons, those are the positively charged ones. So 17 pluses. And I've got 18 electrons plus 18 minuses, means that I get an overall of -1. Okay, so our mass number goes on top, that's the 37. Our atomic number goes on bottom, that's the 17. And if we only have a single charge, so a 1 plus or a 1 minus, we don't actually write the 1. So I'm just going to say chlorine minus. Okay, and that does it for this video. If you'd like to continue on your own, you can work on the speed drills. But as I've said before, the speed drills do not count. They don't go with the lecture worksheets, so that is entirely your own deal. If you want to play with the speed drills, great. Otherwise, we'll see you again in Chapter 4.